All right, here we go. We are on assignment. Oh, sorry, scroll up here. Assignment 4F today, and this is going to be a concept of related rates. Related rates. So before we get going here, what this is dealing with is you'll see what I mean, but the key to success with this thing is to recall the idea of implicit differentiation. Again, as a reminder of what implicit differentiation is what do you do when you have an equation that has both x and y in the same equation? Let's say it's equal to this. And so let's say I'm taking this derivative with respect to x, right? With respect to x. That means technically whatever I'm taking a derivative of gets a dx with this. So for instance, very technically what this answer is 2x, and because I took a derivative of the x, that'd be dx plus 2y. I took a derivative of y, so that's dy dx, and then the constant is 0. Now, we don't report a dx dx. That's the same thing as saying 1. So thus, our answer is dx plus 2y dy dx. And then we clean it up and we isolate dy dx, etc., etc. That's all fine and dandy. But let's say what we're going to be doing today is the same idea of an implicit differentiation, but we're not taking it with respect to x or respect to y. What we're doing is we're taking it with respect to some other letter, like t or something, like time, something like that. So if I am going to take this derivative with respect to t, again, I do all the same divisions, so differentiations, so 2x, because I just got a derivative of an x, that gets a dx dt. So you still take the derivative of it, but you put on this dx dt. And a lot of times what these derivatives are with respect to time is a rate of something. It's like a velocity of purely the x, where x itself is like a position. It's a value at something, and then the dx dt would be the rate at which x is changing. All right, so implicit differentiation, because I'm taking it with respect to time, when I take the derivative of something, like, hey, I'm taking the derivative of this x, which you do, but because I took a derivative of the x, you get a dx dt. Okay, so we want to find dy dt. So we're going to take a derivative with respect to t. So right now y is equal to x to the 1/2. Right now. Okay, so derivative time. Let's take this with respect to t. So derivative of y is 1. So 1 dy dt is equal to 1/2 x to the negative 1/2. I just took a derivative of the x, so dx dt. So cleaning this up just a little bit, we are left with dy dt is equal to 2 square root x dx dt. Okay, so that's cool. Now they give us some values to use. They want to know what is dy dt. All right, so what is dy dt when x is 4 and dx dt is 3. And so this is what, 3/4. All right, same question, but they want to know what is dx dt when x is 25, dy dt is 2. So I'm going to steal this equation right here. I'm going to steal that equation. And so they say dy dt is 2. X is 25. And we want to know what is dx dt. So that's 1/10 times 2, so that's what, 20? As such. All right, number 3, we have xy is equal to 4, so let's take that derivative. So the derivative of x is dx dt equal y alone, plus, leave the first alone, derivative of y is dy dt, and then the derivative of 4 is 0. Now, it appears that they didn't give us enough information to answer our question. So take a look at what they want and what they give us. So they say, hey, find dy dt when x is equal to 8 and dx dt is equal to 10. They want to know what is dy dt. So there's a missing piece. What the heck is y? All right, well, to get that y, in essence, they're not playing games. They straight up give you an x. So you can pretty much figure out y to use. So if x is equal to 8, this implies that 8y is equal to 4, thus y is equal to 1/2. So you just go back to your original equation and figure out where they're talking about. So y is 1/2. So 1/2 of 10 is 5 minus 5 is -5 divided by 8. This implies that dy dt is equal to -5/8. All right, same problem, just different numbers. So here x is equal to 1. So again, what does that imply about my point? So if x is equal to 1, that's 1y is equal to 4. Okay, that's the point. So y is now equal to 4 when x is equal to 1. All right, but again, back to the business at hand. So we want to know what is dx dt. So y is 4 plus x, which is 1. dy dt is -6. And that's all equal to 0. -6, +6 divided by 4 is what, 3/2? Okay, in exercise blah, 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 point is moving along the graph of the given function dx dt, find dy dt for the values of x. All right, so this is somewhat of a more realistic situation. So they want to know what is dy dt at all of these different things. All right, so let's just take this derivative in general. So the derivative is dy dt is equal to 4x dx dt, and then plus 1 goes to 0. So that's our derivative. And they give dx dt as being 2 centimeters per second. So So I believe, excuse me, this is dy dt, not dx dt, I'm sorry. So this is consistent throughout, so this is going to be 8x, and so dy dt in this case is going to be equal to -8. Again, this is centimeters per second. Centimeters per second. When x is 0, dy dt is going to be equal to 0 centimeters per second. When x is equal to 1, this is going to be 8 centimeters per second. Okay, the radius r of a circle is increasing at a rate of 4 centimeters per minute. Find the rate change of the area when radius is 8 centimeters, radius is 32 centimeters. Okay, so area of a circle is pi r squared. So what we're going to do is we're going to take a derivative of this with respect to time. So the derivative with respect to time would be dA dt. So that's the change in area over change in time. So that's the rate of the area is equal to, and now I'm taking the derivative of the r, so that's 2 pi r, and then dr dt. So that's the derivative with respect to time. Okay, so it says that the radius of the circle is increasing at a rate of 4 centimeters per minute. What the heck did that just say? So the rate of the radius, so that's dr dt, is increasing at 4 centimeters per second. So dr dt will be a positive 4. If the radius was getting smaller, it'd be a negative 4. Right, so they provide that as kind of groundwork for here, and they want to know how is the area changing. So let's just kind of go ahead and use this. So dA dt is going to be equal to 2 pi r, in this case that's 8, dr dt, which is 4. And that's 64 pi, right? 8 times 8, yeah. 64 pi, and then an area would be centimeters squared. And then this is a rate, so and I think we're talking about minutes. So that's how much bigger at that moment that the radius is 8 centimeters, that's how fast the area is getting bigger of the circle. All right, part B is the same question. So dA dt is equal to 2 pi r dr dt, which is 4, and I need a calculator on this one. So 2 times 32 times 4 is 256 pi centimeters squared per minute. The volume of a sphere. The volume of a sphere is what, 4/3 pi r cubed, I think? Pretty sure that's right. 4/3 pi r cubed. Let me, I'm almost sure. Four-thirds pi r cubed. Nailed it. Okay. 4/3 pi r cubed. All right, so find the rates of with the volume is changing, and it says the radius is increasing at 3 inches per minute. Okay, so derivative, so dV dt, and again, now I'm paying attention to the r, so that's times 3 So that gets rid of that denominator 3. So that's 4 pi r squared. And then because I took the derivative of the r, that's dr dt. So what is the rate of the volume when this is taking place? And again, what they say is the sphere, the radius is increasing at a rate. So that's a derivative. So the radius at a rate is increasing 3 inches per minute. So here we go. dV dt is equal to 4 pi r squared dr dt. So that's 4 times 81 times 3. And so this volume, I'll shrink it here in just a second, is 972 pi. Volume is inches cubed, and the time is minutes. So that is the volume changing over time. Second one, same question. It's going to be a crazy big number though. So dV dt is 4 pi r squared dr dt, which again is 3. Crazy big number. 15552 pi. Again, that's inches cubed per minute. Explain why the rate of change of the volume of that's supposed to be a sphere, is not consistent even though dr dt is. Well, just think about that. Like think of I think of it as an easier concept, like a pizza. What is the area of that pizza? Now, what if this was increasing at a rate of 2 inches per minute or something like that? How big is the pizza in a minute? Well, it's that much bigger. So think about all the area that it just gained. Okay, that is all the area that pizza gained in a minute. Now, take this pizza and give it 2 inches per minute, and which gained more area? The second one obviously gained more area. Okay, the area of the shaded purple of the right-hand picture is way bigger. So it's just because of the ball is bigger. That's why it's not. It's why it's not consistent. Like the volume will grow exponentially faster. Well, why is because the physical size, the volume, is changing at it's radius squared. So the radius is getting bigger, and so yeah, it's explain why the rate of volume of the sphere is not constant. Well, it's because the radius is squared. That's why. So like bigger sphere equates to bigger volume. Like the pizza idea. The edges of a cube expand at a rate of 6 centimeters per second. How fast is the volume changing when its edges are, et cetera, et cetera, et cetera. All right, so a cube. A cube is length times width times height. All right, so the volume is is equal to, I'll call it S or whatever, sides cubed. Okay, sides cubed. So they're all the same because it's a cube. So the derivative of this is dv dt 3s squared ds dt. Where s again is the length of a side. The edges are expanding at a rate of 6 centimeters per second. So that means the sides are expanding at a rate of 6 centimeters per second. So the first question is what is the volume changing when the side is 2 centimeters? So the volume is changing, that's the rate, is 3s squared ds dt. So that is 412, 672. And this is volume per time. Let me just double check that. Yeah, 72. All right, same question, 10 centimeters. So that's 118, 180. At a sand and gravel pit, sand is falling off of a conveyor onto a conical pile at a rate of 10 cubic feet per minute. So that's a volume. That's a rate. That's a volume change. All right. The diameter of the base of the cone is approximately 3 times the altitude. So it's a big base, and so if this is the altitude, the diameter of the base is approximately 3 times the altitude. At what height, at what rate is the height of the pile changing when the pile is 15 feet high? Okay, the volume of a cone is that. Okay, so note that this is the diameter, and thus the radius would be half that. Radius would be half that. Or I'll show you what this is. All right. So volume is equal to 1/3 pi r squared h. Okay, so we want to know about the height. So I'm going to relate all of this to the height. So the radius is 1/2 the height. Okay, so the radius is 1/2 the height. No, excuse me, I'm sorry, is 1.5 the height. Sorry, that did it up. Just get it right there. Okay, so the diameter of the base is approximately 3 times the altitude. Okay, and that's the height. Okay. So let's see what we got here before we do any funny business. So we got 1/3 pi. This is 9/4 h squared times h. So this is ultimately, this will simplify. So this is what, 3/4 pi h to the third. Okay, so that is our volume. Okay, so let's take the derivative of this. So derivative of volume with respect to time, multiply by 3, so that's 9/4 pi h squared. I just took a derivative of the h, so that's dh dt. Okay, let's see what stuff they give us. So they say that the sand is falling on at 10 cubic feet per minute. That's a volume. So the change in volume of this pile is changing at 10 cubic feet per minute, positive 10 cubic feet per minute. And they want to know what is the rate of the height. So they want to know what is the rate of the height, question mark, when the height is 15 feet high. So dV dt is equal to 9/4 pi h squared dH dt, and that's the question. How is the height changing? How is the height changing? Great googly moogly. So we got 10 times 4 divided by 9 divided by 15 squared. Let's turn that into a fraction. And then it'd be also divided by pi. Yeah, so a lot of times you get these wicked small numbers. Coming out of here. And so this is the change in height over change in time. So this is, what are we talking about here? Feet or something? Feet in minutes. So this is going to be dH, so that's feet, change in height over change in time. So that's, it's changing at that feet per minute. If my memory serves me correctly, we are going to be seeing a lot more of these like gravel pit problems and things like that.